We have Mina Nahvi, who will be presenting on acyclic graphs with at least two L+1 vertices being L-recognizable. Mina, go ahead.
Thank you so much. I'm very happy to be here and talk to you about this. This is a joint project with Sasha Kostachka, Doug West, and Dara Zerlin. So I was thinking the best way is probably to just get started with some definitions. So every graph we talk about in this project is finite and simple. The n minus L deck of a graph G is the multiset of all of the induced subgraphs of G that we obtain by deleting L vertices. So we have n choose L ways of deleting L vertices from a graph on n vertices. And looking at kind of the list of all those subgraphs, that's what we get as the n minus L deck. And we call each subgraph a card in the deck. And this concept, I think, has mostly been interesting in the sense that what if we don't know the original graph? We don't know what the original graph looks like, but we have a bunch of information about its smaller subgraphs, like we know all of its induced subgraphs of a certain size. Then it's a really kind of natural question to ask, what can we deduce about the original graph? So using all these local information, what can we deduce globally? That's why an n-vertex graph G, we call it l-reconstructible, if by looking at its n minus L deck, again, the set of all the subgraphs that we get by deleting L vertices, we can kind of put the pieces back together and reconstruct the original. Also, a property of graphs, whether it's connectedness or acyclicity, which is what we mainly talk about in this project, any property, we will call it L-recognizable if from looking at the n minus L deck of the graph, we can tell if that graph, and not just one graph, any graph, we can look at the n minus L deck and tell if it has that property or not. Finally, a family of graphs like, I don't know, trees or disconnected graphs, any family, we call it weakly L-reconstructible if there are no two graphs in that family that have the same n minus L deck. In other words, that kind of means that if you have the extra information that a graph belongs to a weakly L-reconstructible family, that means that using that information, you can reconstruct it. So before we get into the results and the proof ideas, I wanted to just make some observations and talk about an example with you. When we delete L vertices from the graph and we look at that deck, we lose more information compared to when we delete fewer vertices naturally. And that's, we can see that just by counting arguments from having the n minus L deck, we can get all of the bigger decks, basically. So the deck that we get by deleting L minus 1 vertices is kind of, we can reconstruct it from the n minus L deck. So if you think about the deck of the graph, that every induced subgraph in it has two vertices, that deck gives us the number of edges. So basically, we usually can reconstruct the number of edges by looking at whatever deck we're looking at. Finally, I wanted to show you, let's take a look at these two different graphs. The one on the left is C4 plus one isolated vertex. The one on the right is just what we get from subdividing one of the edges of the star on 4 vertices. And these two, we can see if we spend a couple minutes looking at how can we delete 2 vertices from each of them, we can see that they both have the same deck. So they both have 4 of these cards, 2 cards that are just 3 isolated vertices, and they both have 4 cards like this. So this is a very small example, but it shows that it's not an obvious thing that graphs would just have a unique deck for whatever L we're talking about. Okay, moving forward. The main reconstruction conjecture came from Kelly and Ulam in 1942. And back then they thought that there has to be a threshold for the number of vertices such that all graphs with at least that many vertices are one reconstructible. Again, what that means is we're deleting just one vertex. So we have n different subgraphs of the graph, and they think at some point, like for large enough n, we should be able to reconstruct it. Even though it's been a very long time since that conjecture, it hasn't been proven or disproven yet. And Kelly kind of introduced a more general version of this conjecture in 1957, saying that this is probably not, this is probably true for any L. So no matter how many vertices we're deleting, if the number of vertices of the original graph is large enough, which will depend on L, that threshold, then we can reconstruct the original graph. So we're gonna talk about reconstruction of trees for a second, because mainly in this project, we focus on whether we can tell from the deck if the original graph had a cycle or was it acyclic. And trees are just, you know, the connected acyclic graphs. So we do know that every tree with at least 3 vertices is one reconstructible. I think there's actually like a somewhat short proof for that. In 1976, Giles proved that every tree with at least 6 vertices is 2 reconstructible, which the example that I was talking about in 2 slides ago, this shows that that is sharp, because here we have a tree on 5 vertices, the graph on the right, and it's not reconstructible, 2 reconstructible, because it shares the same 3 deck with the graph on the left. So as a more general conjecture for trees, Needle in 1990 conjectured that every tree with at least 2L plus 1 vertices is weakly L reconstructible. Again, that means that if we know we're looking at the deck of a tree, then we would be able to reconstruct it. So our main result in this project is that we showed that when n is at least 2L plus 1, except when L is 2 and n is 5, which again, it doesn't work because of the same example. The n minus L deck of an n vertex graph determines whether the graph contains a cycle or not. So the reason why both, if Needle's conjecture is true and our theorem, both are sharp, is because you can see below, if we look at a path on 2L vertices and the disjoint union of a cycle on L plus 1 vertices and a path on L minus 1 vertices, they both have the same deck. It's not immediate to see, but there are proofs for it. So the 2L plus 1, if true in the conjecture, is gonna be sharp. So I want to tell you just a little bit about the proof ideas because we don't have that much time, but the main thing is that when we were trying to prove this theorem, we realized that when n is actually equal to 2L plus 1, there's a lot of, like, we have to do a lot more. We have to struggle a lot more to prove it. So we ended up kind of proving them separately using similar ideas, but the 2L plus 1 case is much longer. But if we can assume that n is at least 2L plus 2, then these are the main ideas that we use. So as a reminder most of you probably know, might have heard of these concepts, but just as a reminder, in a graph G, the longest distance between any 2 vertices is called the diameter. And then for any vertex in G, we look at the vertex that is farthest from that and measure that distance. And then among all the vertices, those that have the smallest possible largest distance are called the centers of G. And radius of G is that minimum maximum distance that I just told you about. So these are some concepts, like we came up with these names because we needed something like that. So let's say we fix a vertex in a graph G. The K ball, and K is just some integer. The K ball at V is the subgraph induced by all vertices within distance K of V in that graph. kind of following the botanical theme of, trees, forests, leaves, stuff like that, we decided to call a tree with diameter 2K a K-vine. And then a K-center in a graph is a vertex that is the center of some K-vine. Those are just fancier words for saying that a vertex in a graph is a K-center if there is some path with diameter 2K in that graph, that this is the middle, like the central vertex. Similarly, sorry about that, I had to drink some water. For any edge in a graph G, the K ball at edge E is the induced subgraph on all the vertices that are at distance at most K from either one of the endpoints. So a K vine is a tree with diameter 2K plus 1, meaning that edge is right in the middle. And then the K central edge, a K central edge in G is an edge that in simpler words, there is some path of length 2K plus 1 that this edge is right in the middle. So why am I telling you all this? It's because this is how we went about the proof. By contradiction, we assume that we have some forest on n vertices and some graph on n vertices, which is not a forest, meaning it has at least one cycle. Then we assume that they have the same deck of n minus L vertex induced subgraphs. We call that deck D. Then because we were assuming they share a deck and F is a forest, that means none of the decks are going to have cycles in them either, because they are all subgraphs of the forest. So all the cards have to be acyclic, and also any cycle in H has to be too big to fit in a card, meaning any cycle has to have at least n minus L plus 1 vertices. Then we defined K hat to be the smallest radius in all of the cards that we can see. And then we fixed K to be K hat minus 1. Then we proved these two lemmas. Unfortunately, there's not enough time for me to tell you how we proved them, but we basically first showed that, again, this is all for the case that n is at least 2L plus 2, that the deck cannot have any card in it, that the diameter is 2K plus 1. And then using that lemma, we proved that F and H, they both have to have the same number of K centers and K central edges. And that we can deduce, like we can compute these two numbers from the deck. So I think I have a little bit more time. So I'm just gonna kind of tell you about another result that is very recent. Before I tell you about that, I want to say that Needle's conjecture, which was that he conjectured that every tree, basically trees are weakly L-reconstructible when n is at least 2L plus 1. And because we proved that when n is at least 2L plus 1, from the deck, we can tell if we have a cycle or not, kind of with the fact that we know the number of edges, then we can combine these two and say this is the new conjecture. It's equivalent now to Needle's conjecture, but it's really about trees being L-reconstructible when n is at least 2L plus 1. A very recent development is this paper that is very recent by Groenland, Johnston, Scott, and Tan. And they obtained a very interesting result about general L. And they're saying basically if each card is at least this size in terms of n, then the tree is going to be L-reconstructible. So this bound is far from what we think is the sharp bound, which is 2L plus 1 because of Needle's conjecture. Because as you can see, they are deleting less than a ninth of the vertices because it's 8n over 9, sorry. They're deleting less than 1/9 of the vertices, and Needle's conjecture said we can push that until like almost half of the vertices. But I think that is the only thing known for general L in terms of trees. So I was thinking I could finish by just saying what I think are some problems that we can think about if you're interested in this topic. I think because for one, reconstructibility of trees, and two, reconstructibility of trees, we know the sharp exact bound. We could, if they have a short proof, I think it would be interesting to know the sharp bound for three, reconstructibility of trees as well. And also, as I said, this bound, the only bound that we have for general L is far from what we think is sharp. And I think pushing for that to improve that in any manner would be interesting. Thank you so much for your time.
All right, so let's go ahead and thank Mina with our Zoom adapted versions of applause. Great talk.
Thank you.
Would you mind just going back one slide for another moment to the open problems slide? I just want to take a closer look at what is your
sorry, this one
here. Yeah, that one. And in the meantime, see if there are any questions from the audience.
This might not be a very good question, but has anyone ever looked at, so your decks are multi-sets. What if you just didn't look at, does that make sense? Multiplicity? Like what if you looked at what's present?
Oh, you're saying what if we have less information, so we don't know the multiplicity?
Yeah, has anyone ever done that? Or
I don't know, that's an interesting question. I'm not sure right now if someone has done it or not, but yeah, I'm interested to know that as well. I haven't heard of it, but it might very well be a thing.
Cool, thanks.
If anyone is interested in knowing more about this proof, in case, I'm just putting the link to the paper on arXiv in the chat.
Yeah, that's actually very helpful. I'm glad that you had done that. If I find time in it being fast approaching University of Tennessee's final exams week, I kind of want to take a closer look at that. And others in the audience may as well. All right, so are there any other questions? All right, if not, then let's thank our speakers again.